This playlist deals with some aspects of Eurocode 2 version 2023. The video is about clause 9, serviceability limit state, and in fact, it will deal with Annex S, S4, which is the simplified control of cracking. Instead of using those lengthy formulas for calculating crack width, you can also simplify it by using Annex S. In Annex S4, there will be there's a formula S6, and it gives you the diameter of rebar that you should use a smaller diameter of rebar given by this formula. And this formula depends on different coefficients. It depends on the value of the crack width that you want to achieve, and of the steel stress in the rebars, and of course of the concrete cover. Now we will see that the coefficient K fleur, we have seen that before. This is the coefficient in the previous slide, and it was a different value than what we've seen here. That's why they call it K fleur simple, or it's a simplified control of cracking. So it's a little bit confusing why those two, why the coefficient is different. But anyway, it's clear. When one phase is in compression, it's 1 minus 3.5 AY divided by H. And if both phases are in tension, it's 1. Now, I'm wondering why make it so difficult? Why don't we say with bending it's this and in tension is that? So it's a little bit odd that they have this formulation. You see again, KB, the factor of the bond, we've seen that before, but now it's KB simple, and it's 0.9 and 1.2 is exactly the same as KB. So why don't you put it KB instead of KB simple? K1 over R simple, it's a total, K1 over R was defined in the other slides in a different formula, but now for this formula S6, they have made some interpolations of the formulas to simplify the formula, to make it an explicit formula. So that's in fact an interpolation. And for bending, it's given by this formula. For tension, it is 1. You see in this formula here, it's A, Y, and A. So this is a little bit confusing too, but I think it's a typo. A is equal to AY, and it's the distance from concrete surface to the center of the first layer of the bars. We also have here rho, and it's the reinforcement ratio, which is given as the total reinforcement divided by, and now this I do not understand. Why is it divided by BD? Until now, it is or divided by the concrete cross section, or it is divided by AC effective. And we have seen in the previous slides that for first cracking, it's divided by AC, where the steel stress equals the yield stress. And for subsequent cracks, it's AC effective, where the steel stress is smaller than the yield stress. So this is the general principle that we use. But suddenly, in formula S6, they use another reinforcement ratio and they use BD. So this is not very sensible. So this is the formula. And there's another factor, sigma S, which is the stress permitted in the reinforcement closest to the most tensioned concrete surface after formation of all cracks. So this is the stress permitted. What does that mean? It's not a calculated stress then. What is it? Is it equal to sigma S limit? Or so it's confusing. Why do they use stress permitted? Reinforcement closest to the most tensioned, okay. So it means, is this formula only valid for multiple layers, or are we using the same principle that sigma S is always the steel stress in the rebar layer, which is closest to the concrete surface? And after formation of all cracks, so this means that you have a subsequent cracks, and this will indicate that you have to use AC effective, which is not the case in rho. So now this is a contradiction. When all cracks are formed, then rho should be defined according AC effective. So it's not very consistent. And then the code says sigma S may be taken as the calculated stress. It is the calculated stress, okay? According to loads, fine, that's what we expect. Or a lower stress sigma S limit according to formula S4, formula that we have seen before in previous slides. Now, there's a problem with this. When do we use sigma S and when do you use sigma S limit? There's a big difference between those two. But when do we use it? What is the criteria? Remember, sigma S limit, formula S4, is this formula where sigma S limit is a function of the diameter and it's a function of the limitation of crack width that you want to obtain, and it's a function of a FCT effective and the concrete cover. But this is also a function. Here you calculate the bar diameter, but it's also a function of the limitation of the crack width, of the steel stress, which is not in this formula sigma S limit. So it's getting complicated. If you change this sigma S and sigma S limit, then you will have also a bar diameter twice there and there in your formula and here. So this will be very difficult to calculate. The sigma S limit, that sigma S can be taken as sigma S limit, this cannot be right, not at all. And we'll show you why. If you take a simple example of a beam 600 times 300 with the location of the first layer of rebars, and we assume that we have calculated crack width, and the limitation of the crack width equals to 0.2 millimeters. And the reinforcement will take as three bars, which is 3 bars into the width of 300 millimeters, which is in total 3p squared over 4. So n is 3. And now we can calculate sigma S limit for a diameter 16, 3 diameter 16. The sigma S limit is 147 and sigma S is 264, and we take the ratio. We do it for a diameter 16, 20, 25, 32. And we see from this table that the sigma S limit is more or less half of sigma S. So there's a huge difference between sigma S limit and sigma S. So allowing to use both in the same formula cannot be right. This is not good. Also, sigma S limit for the same crack width, that you want to obtain, is sigma S limit a function of the diameter and the concrete quality. On the other at the other end, sigma S for the same crack width requirement is dependent on the number of bars. Sigma S limit is not dependent on the number of bars. And it's dependent on the bending moment, the applied bending moment. Sigma S limit is not dependent on the applied bending moment. And it's dependent of ES over EC. So you can say more or less this is also dependent on the concrete quality. But you can clearly see from this comparison that this cannot be right. So don't use sigma S limit in the formula, but use sigma S. Now we will compare the simplified control of cracking with the more extensive way of calculating crack width of the refined method. So the blue line is the refined method and the red line the simplified method. On the x-axis, it's the applied bending moment. On the y-axis, it's the calculated crack width. And this is for a section 600 by 300 with 3 diameters 20 and a concrete quality of 30. Doing so, you have a linear dependence. And we will see that the simplified method of calculating crack width is much larger than the refined, which we expect that it should be larger, but the difference is quite big. You have a difference in calculating the crack width of 0.1 of a millimeter, which is a lot crack width calculations. And even for large bending moments, you will have a difference of almost 0.2 millimeters, which is very large. We can rearrange the data, and on the x-axis is the bending moment, applied bending moment, and on the y-axis is the simplified method divided by the refined method. And you will see that if you have a calculated crack width of 0.3 or 0.1 millimeter, you will see that for 0.3 millimeters, you will have 60% more crack width opening if you use a simplified method, but it can go up until 2. Until 2, it means until 100% more or 120% more. So using the simplified method of control of crack width, it will consume a lot of reinforcement compared with the calculated method. We can do the same for slabs to see if there is a difference. I've chosen a slab of 250 in depth and 10 diameters 14. Again, the same method. And you will see that the refined method of calculation, if compared to the simplified method, that the simplified method gives you more or less 0.1 more, 0.1 millimeter more crack width than the refined method. We can rearrange the data again, and then again in a graph, bending moment, and on the y-axis, simplified method divided by the refined method. And this is again for the different crack widths. And then you will see that it's more or less constant, 1.75. So the crack width is 75% more if you use a simplified method. But we know in this region, this is the under limit for delta sigma epsilon. And in the other region, it's the other part of the equation that is governing. But again, we will see here 70% and from 30 to 70% more crack width opening, calculated crack width opening. So I would conclude, avoid using the simplified method of S4.